Yeah.
So, hello everyone. It's really a pleasure to announce Mohameden Ahmedou from Giessen, who's our speaker today. And the title of his talk is a new blow-up phenomena for the Nirenberg problem on half spheres. So enjoy, and Mohameden, please go ahead.
Okay, thank you very much. First of all, I would like to thank the organizer for the opportunity to talk in this seminar, and in particular, Philip, who invited me to give a talk. So the topic of today is a quite famous problem in geometric analysis. It is a so-called Nirenberg problem. And so I will report on some recent results obtained jointly with Mohameden Ahmedou from the Sfax University. And so let me first explain the main problem, the Nirenberg problem. Most of you already know about this problem, maybe have already worked on this problem. So this is, everything started with an equation which was raised by Louis Nirenberg in the academic year 1969, 1970. And Nirenberg asked his student, but also the mathematical community, so given a function on the sphere, so you take the sphere with its standard metric, and then you have also a function on this sphere, then you ask, is it possible to find a conformal metric in the conformal class of the standard metric, such that in the case of S2, the Gauss curvature is given pointwise by the function k, and in the case where the dimension is bigger than or equal to 3, that the scalar curvature is given exactly by the function. And this problem has a very nice geometric PDs, also PDs formulation, because if you remember, so let's first start with the case of the two sphere. So remember that if you take a metric, a conformal metric to the standard metric, and you write the conformal factor as exponential at the power of 2u, then the transformation laws of the Gauss curvature and the conformal change of the metric tells you that actually this conformal factor u should satisfy the following PD, namely minus Laplace of u plus the Gauss curvature of the background metric equal to the Gauss curvature of the new metric times exponential to u. And so now you can reformulate the Nirenberg problems and ask, is it possible to find a solution of this following nonlinear PD with exponential nonlinearity, namely minus Laplace of u plus 1, so this is the Gauss curvature of the sphere, equal to k exponential to u. And now in the high dimension, you have also something similar. So namely in this case here, you choose your conformal metric to be equal to u at the power of 4 divided by n minus 2 times the background metric. And then the transformation law of the scalar curvature and the conformal change of the metric tells you that the conformal factor u should satisfy the following equation, namely minus Laplace u plus a constant Cn times the scalar curvature of the background metric times u equal to r, the scalar curvature of the new metric, times u at the power of n plus 2 over n minus 2. And then you can rephrase the equation of Nirenberg and ask, is it possible always to find the solution of the following nonlinear PD, minus Laplace of u plus n times n minus 2 divided by 4 times u equal to k, u at the power of n plus 2 divided by n minus 2. And of course, you ask u to be positive, because otherwise you will not have a metric. So this equation here is a nonlinear semi-linear equation, but the problem is with this nonlinearity. The nonlinearity is critical because n plus 2 divided by n minus 2 plus 1. This is equal to 2n over n minus 2. This is the Sobolev critical exponent. So, and because of this critical exponent, you have that the corresponding Euler-Lagrange functional does not satisfy the Pallas-Meil condition. And this means that standard metric of calculus of variation cannot be applied. From another part, you see that actually this exponent is a borderline. So if you lower this exponent a little bit, so you recover compactness and you recover existence. And one way to overcome this difficulty is to start first by a subcritical approximation. So you take a epsilon, a small parameter, and you consider the following subcritical approximation, namely minus Laplace of u plus n times n minus 2 divided by 4 times u equal to k. Now at the power of u at the power of n plus 2 divided by n minus 2 minus epsilon. And then you recover compactness and you can prove existence of solution. And then now the second step is to say, okay, I will now let epsilon go to 0. And is it possible to recover a solution of my original problem? Then you want to understand the behavior of this epsilon, the convergence of this sequence of u epsilon. And then if you use the elliptic estimates, then you see that actually there are two alternatives. So either the infinity norm of u epsilon is uniformly bounded, and in this case, elliptic estimate tells you that you are bounded in all spaces, and then actually that you will converge in the C2 alpha topology to a function, and this function will solve the Nirenberg problem. So this is the good case. The other case is that there is a blow up in the infinity norm, which means that there exists a point on the sphere such that u epsilon as a point x epsilon, so that u epsilon applied to x epsilon will go to plus infinity. So now, so you have to understand this the lack of compactness, and in this framework, so you have the so-called concentration compactness principle, which allows you to understand what happens to this u epsilon. And so this is a work of Pierre Williams, Michel Struve, Jean-Michel Courant, Chaim Brezis, among others. And it follows from this method here that if you have blow up, that actually you have some kind of concentration of compactness, in the sense that if you multiply the Lebesgue measure with the density u epsilon at the power of 2n over n minus 2, so this random measure here will converge weakly, in the sense of measure, to a sum of Dirac masses times some weights alpha I. And more precisely, you have that at some point where concentration occurs, this point here, if you integrate the norm of u epsilon in L 2n over n minus 2, this norm here will be lower bounded if you let epsilon go to 0. So there is a concentration of compactness in this sense. So, and the reason of this concentration of compactness is that actually when you make a rescaling, you have a function on Rn, and this is a profile of the blow up, and this function satisfies the following equation: minus Laplace of u equal to u at the power of n plus 2 divided by n minus 2, and you, of course, you ask u to be positive. So this equation can be classified, and all solution can be parameterized with n plus 1 parameter. So you have the location, so A, so this is the location of the bubble, and then the height of the bubble. So these are bubbles with a point, a center of the bubble, and you have a height here. This height here can be very, very, very large. And So this kind of function here, they have the same kind of behavior that the function u epsilon. Namely, if you take delta I lambda at the power of 2n over n minus 2 times the Nirenberg measure, you converge weakly in the sense of measure to Sn times the Dirac mass, where Sn here is a universal constant, and we call it the energy. So this bubble here, they come with an energy. And so now you can do something more refined, and then you try to understand the behavior of this blob. And in this respect here, this was initiated by Richard Schoen, although the approximation itself is already in the paper of Yamabe from 1960. But actually, this refined blob analysis, this goes back to Rick Schoen, and Rick Schoen has a typology of this blow up. So first, if you have a point where there is a sequence A epsilon, which converges to this point here, and u epsilon of A epsilon goes to plus infinity, so you say that this point here is a blow up point. So you may have many sequences, but at least if you have one, so you say that this is a blow up point. And so this blow up is called isolated if you take this blow up point, and so if they are separated. So if in every blow up point, if every two blow up points are far from each other, yeah, in the sense that there is a eta, so that the distance is lower bounded by some eta positive. So this means that there is no continuum of blow up points. But there is another point here, because here we defined the blow up so that there is a sequence. But what happens is if we have many sequences converging to the same point, and this is another definition, which is called a simple. So if we call it simple, if there is only one, and actually how we can quantify this definition here. So we can look to the integral of k u epsilon at the power of 2n over n minus 2. So if it is only the energy of one bubble, so you say that it is simple. But we will see that, so if it is non-simple, you get at one point the energy of m bubbles, m bigger than or equal to 2. So now if with this definition, let us come back to the Nirenberg problem. So this is a very long story, which starts with Rick Schoen and some unpublished notes, and then later developed by Yang Li, by Shen and Lin, by Druyer, Hébert Robert, among others. And usually you assume the following non-degeneracy assumption. You say that at every critical point of k, Laplace of k should not be equal to 0, and we call it non-degeneracy assumption. So under this non-degeneracy assumption, so you know first that all blow-up points should be critical point of k. So this means that the location of the blow-up point is known. So every blow-up point should be a critical point of k, and also the Laplace of k at this critical point should be strictly negative. So this is in general, but you can be more specific if you look to the dimension. For example, if the dimension is 2 or 3, you know that there is only one single blow-up. So if you have a sequence of solution, blow-up, big solution, the u epsilon will blow up only one time. And all these blow-up also are simple. And then now, if n is bigger than or equal to 4, you may have you do have actually generically multiple blow-up, but they are all isolated. So this is a very long history. So it starts with a paper with Yang Li in 1996, where he proved this claim for n equal to 4. And then for n bigger than or equal to 5, he made some flatness condition. So it violates actually this condition here. because flattened conditions are not generic conditions. So this is generic condition. So this is satisfied for almost every function. And then the full picture was only recently fully understood in a paper published by Andrei Malchiudi and Martin Meyer. The reason for that for n bigger than or equal to 5, the situation is quite complicated because you may have the situation that you have the so-called mixed blow-up, which means that you have omega, a solution, plus a sum of bubbles. And then this makes blow-up quite involved and quite complicated. So this is the situation for the Nirenberg problem on the spheres. And now my topic today is on some related problem, which is what happens if we consider a manifold with boundary. So in this case here, if we consider the half sphere. So of course, I forgot to say that this problem can also be posed on any manifold, in particular on compact manifold. But usually the spherical case is the most difficult one, because usually if you have some geometry, so this geometry can help you to rule out the blob. But if you are on the sphere, so there is no help coming from the geometry, and then you have really to understand what happens to your blowing up solution. So the problem is the following. So if you are on a manifold with boundary, then you have the scalar curvature, but you have also the mean curvature, and you have to prescribe them in a simultaneous way. And one way to reformulate this kind of problem is to say, okay, I will prescribe the scalar curvature to be a function, and then I will assume that the mean curvature is equal to 0. So this is prescribing the scalar curvature under minimal boundary condition. And then you look to the transformation of the scalar curvature. So this is what we have seen, but also there is a similar transformation law of the mean curvature under the conformal change of the metric, and you end up with this boundary value problem, minus Laplace of u plus n times n minus 2 divided by 4 times u equal to k u at the power of n plus 2 over n minus 2. U is positive, so this is very similar to the equation that we had on the sphere, but then on the boundary you have a Neumann boundary condition. So this is also a non-compact problem, because also you have always this Sobolev exponent, and one way to overcome such a difficulty is to lower the exponent by considering first a subcritical approximation, namely minus Laplace of u plus n times n minus 2 divided by 4 times u equal to k u at the power of n plus 2 divided by n minus 2 minus epsilon, u positive, and the normal derivative is equal to 0 on the bottom. Then you can now analyze also the asymptotic behavior of u epsilon using elliptic estimate up to the boundary. And so what you find is something very similar to what we have already seen for the closed case, namely there are two possibilities: either the L-infinity norm of u epsilon is uniformly bounded. In this case here, you have a convergence in the C to alpha topology, and the limit is the solution of this Nirenberg problem here on the half sphere. In the other case, you have a blow up, and if you have a blow up, then you can analyze the lack of compactness. You can use also constantation compactness principle, so you get something similar. The only difference is that now u epsilon at the power of 2 and divided by n minus 2 times the Nirenberg measure will converge to a sum of Dirac with some weight. Some of them are sitting in the interior, and some of them are on the boundary of the sphere. And then you have a concentration of compactness in the sense that the norm L at the power of 2 and over n minus 2 will concentrate. So if you integrate on a very shrinking balls, you have always a universe constant which minimize your integral. So this is something similar to what happens in the closed case. The only thing is that now you have you have points which are in the interior, and you have also points which are on the boundary. Okay, so and the reason why you find also this kind of concentration of compactness is due to the fact that if you make a scaling for a point going to the boundary, then you get a bubble, but a bubble sitting on the boundary. And the only difference here is that this bubble here will have the half energy of a bubble which is in the interior. So this is the only difference. Okay, now what about the blow-up analysis? So this has been done for low dimension. Low dimension have spheres. And then now you need also a non-degeneracy assumption, which is somehow similar for a critical point. It is the same that the one that you have for the closed case, namely that at every critical point, Laplace should be not equal to 0. But then you have the boundary, and on the boundary, you have to first consider the restriction of k on the boundary, and then so you assume that every critical point of this restriction satisfies that the normal derivative does not vanish. Okay, so exactly like in the closed case, this is the most difficult situation. So if you assume that it is not satisfied, so then it is easier. So in this case here, something is already known for low dimension, namely for S2 plus. This I didn't mention here, but this is already known for S3 plus and also for S4 plus. Here the situation is that here you cannot rule out. I mean, here there are multiple blow-up, even on the this is plus here. This is the no, this is not plus. I'm sorry for that. Sorry for that. No, this is if you are in the interior, then what you can prove is that the gradient should be equal to 0 and Laplace should be strictly negative. And if you are on the boundary of Sn plus, then this is a critical point of the such that this is a point such that the tangential part of the gradient is equal to 0 and the normal part is positive. So this is the situation when you have a boundary. And then for n equal to 3 and 4, it has been proved. So there is a paper that I wrote many years ago with Jadli and Malkiudi, where we proved also, among other things, that on S3, all bubbles, you may have multiple bubbles, but they are all isolated and simple. And later, Ben Ayad, Goody, and Wildeboe proved that something similar also on S4 plus. And now our goal here was to analyze what happens for the high dimensional half sphere. So we have seen that for the case of closed sphere, it took more than 20 years to understand the full picture, and we wanted to understand also the same picture on the half spheres. So in this situation here, so you start first analyzing what happens for your epsilon, and then a first result that you can prove is some kind of Struve energy decomposition. So this has been proved by Michael Struve in 1984. And then for the Yamabe problem and Yamabe type problems. But so the same kind of decomposition also can also be proved here for our equation. And then we proved that actually you can decompose if you have a U epsilon blowing up solution. So first, there is two difficulties here. There is two cases. First, there is a case where U epsilon converge weakly to a solution, to a function, and this function will be a weak solution, and by regularity will be a solution. And there is another case where you converge weakly to 0. So I will concentrate on the case where the convergence has a 0 weak limit. The other case also can be treated similarly. In the paper, we also treated both cases. But let me just concentrate on the case where U epsilon converge weakly to 0 and emphasize the differences between the blob picture on the sphere and the blob picture on the half sphere. In particular, we have seen that on the sphere there is no non-simple blob, and we will see that on the half sphere there are situations where you can you do have simple blob, and actually you can construct simple blob. So the starting point is that this is a Struve energy decomposition. So you can decompose your epsilon into some of bubbles sitting in the interior and some of bubbles sitting on the boundary, plus some error term, which is very small in the H1 norm. And so now let me fix this terminology. So AI are called concentration points. So they are not blob points, because this concentration point may converge to the same blob point. So you remember. And then lambda I is called the speed of the concentration. And then there is another interesting quantity, which we call epsilon ij. This is the mutual interaction between two bubbles. And what we can prove that this interaction is always very weak. It goes to zero. So now what happens? First, let us look to what happens for the interior blob point. So interior blob point will converge to a critical point of K with Laplace strictly negative. So this is the same situation like in the sphere, like also in the half sphere for the low dimension. And what we can also prove is that there is an estimate of the height of the speed. So the speed here, the speed lambda I behaves like. I'm sorry. Let me. So I'm not. So this I'm not able now to write. I don't know why. So and anyway, the lambda I will behave like 1 over the square root of epsilon, because this is positive. So the Laplace is negative. So this is positive. So this is a constant, and so the height will be 1 over the square root of epsilon. And then you can also prove that at every blow-up point, there is only one sequence converging there. So it is really isolated simple. So here you get the same situation as what you get for the closed case. So this is the situation. Now, what happens for the boundary blow-up point? So boundary blow-up point will converge to critical point of the restriction of K on the boundary, and they will satisfy that it is that the normal derivative now is positive. And also there is something interesting here. Now the height is different, because here you can get lambda I now behaves like 1 over epsilon. Before we get lambda I behaves like 1 over the square root of epsilon. So because of this difference of behavior of the rate of a concentration, one is able to prove that in some situation you will have non-simple blob. But then let us study further this blob point and look to their nature. So if you have now a blow-up point, a boundary blow-up point, then and then this means that you have at least one concentration point converging there. Then you look to this expression here, lambda I, so the height of the speed of the concentration times the distance. So if this is uniformly bounded, then you can prove that it is an isolated simple. If this is not bounded, then you can prove that it is not isolated simple, that there exists at least 2 concentration points, concentration sequences converging to the same point. So this is a first 2 alternative. So either you have this one here and then it is simple, or you do not have it and it is non-simple. But we want to understand more. So this is only a kind of 2 alternatives. So is it possible that we do have this alternative? Yes, but for this we need actually to understand more about this non-blow-up point, and actually to understand the nature of of a boundary blob point with respect to the simplicitness and non-simplicitness, we make use of some Hamilton function, so it's sometimes called also Kirchhoff-Roth type functional. And this function is quite, this is what you find if, for example, you are looking for the location of vortices in the Euler equation. Or if you look to the concentration point in the mean field equation. And then it is very surprising that something similar, some family of the same type also arises to understand the non-simple blob behavior in these Yamabe type problems, in the Nirenberg problem. So this function here is defined on the on the configuration space of the tangent. So you take a point on the boundary, and you take the tangent space, and you consider the configuration space of order m. So this means all the point xi xj, so that xi is not equal to xj. And then you define your function to be 1/2 of the Hessian matrix of K1 applied to xi plus some kind of Coulomb potential. So it's very surprising that this physical quantity here arises in a pure geometric context. So what is the relation between this Hamilton function and your non-simple blob? So if you assume that you have non-simple blob situation, so you have a point which is non-simple blob, which means that you have more than one sequence converging there, then you can rescale. So what you do is that you rescale the distance of ai zi times 1 of epsilon, and if you rescale it, they will converge to critical point of this function here. So in particular, if you know that that this function here does not have any critical point, then you can rule out non-simple blob. And if you know that it does have critical point, then you can try to construct also different sequences converging to the same point. And so this is not the whole story. The whole story is that actually our aim is to analyze this problem from a very variational viewpoint. And for the variational viewpoint, you would like to understand the contribution, topology contribution of blowing up solution to the difference of topology between the level set of the function. And like in Morse theory, and like in any extended Morse theory, what plays here a role is the Morse index of this solution. So this solution here will attach, when you cross some kind of a critical level, you have to attach a handle of dimension the Morse index. And actually what is here surprising is that we can also compute it here. So for the interior point, for a boundary blob point, which is isolated simple, you can compute it, and this is m-1 plus the sum of the co-index of K1 at A1. So A1 are critical point, and then you look to their co-index. If you have now non-simple blob point, then you have to change your K1 by FZM. So this function here, so it appears because we did this scaling, but actually this is more relevant, because if you want to compute the topology, then you have to use it to use this function here. So it is inherent to the problem. So this is something which is canonically defined by this problem here. Now the next question is what about the critical point of this function here? Okay, so this function may have or may not have critical point, and so let me here point out some simple situation. So if your z is a local minimum of the function K1, then you can prove that you have always a minimum, that the function has always a minimum. So if now z is a local maximum, you can prove that the function does not have any critical point. So this means that if you have a local maximum, you cannot build there more than one bubble. So this means that every local maximum of K1 is a simple blob. And now you can also give a condition on the Hessian matrix so that you have a critical point and even a non-degenerate critical point. So this is the situation of this function here. And now let us look to the situation in the other direction. We proved now there are some possibilities to have non-simple blob, but these are only alternatives. Now we want to say that actually you can construct non-simple blob, and I gave here three type of this construction here. In the paper we gave actually all the construction, because from one part we perform a blob analysis to see all the situation, and actually for each situation we prove that actually this there is a construction. They all occur. This alternative only can occur, always can occur. So if you take now a function k, which is a positive, and you take n bigger than or equal to 5, so this is very important, you take a non-degenerate critical point of K1, which is not the local maximum, because we have seen that local maxima, for local maxima, the corresponding Hamilton function does not have any critical point. So there you cannot construct any non-simple blob. So this is the first condition. The condition is that if you assume that the Hessian matrix has at least one simple positive eigenvalue, then you can produce a solution of P epsilon concentrated at Z with the energy of two masses. This means that you have two sequences converging there. So this is the first situation. The next situation is that you can now make an assumption on the function FZM. So every time, so this is the first assumption. I do not repeat them because this is a necessary assumption. So you take a critical point of K, which is not a local maximum, and satisfying this condition, because otherwise you know that there is no concentration at this point here. But if you have such a point where boundary blob point, where it might be that you have a concentration, then you look to this function here. This is this Hamilton function, FZM. If it has, for some m, a non-degenerate critical point, then you can construct there a solution of a bubble with energy equal to m times the energy of the bubble, which means that for every m, you have m bubbles. So for m equal to 2, you have 2 bubbles, m equal to 3, you have 3 bubbles, and so on. And so this is at one point. You can also combine it at many points here. So if you have a situation where you have many critical points of K1, which are not local maxima, and such that also the normal derivative is positive. So these are all necessary conditions to have a blow up. And then if for every Zi, and there is a Qi, such that this Hamilton function here has a non-degenerate critical point, then you can construct now a blowing up solution, which blows up at the point Z1 with Q1 bubble, Z2 with Q2 bubble, and so on. So this means that you can combine all this kind of bubbles. And also, this I didn't write here, but also if you have, because here we assumed from the beginning that U epsilon converges weakly to 0. So if actually it converges weakly to a function omega, then this omega is a solution of the Nirenberg problem, and then you have some kind of mixed bubble. You have omega plus some of bubbles, and these bubbles may in all this situation, assuming this condition on the Hamilton function, may exhibit multiple bubbling at the same point. There is also something, the last feature that also I would like to emphasize. Actually, you can prove that there is a blowing up solution with infinite energy and infinite Morse index. So, and the condition is quite simple. So there are these necessary conditions. So I will not repeat them. So you assume that you have an uncritical point with the normal derivative is positive. Now, if you assume that the Hessian matrix has only one positive eigenvalue and all the other are negative, then for every m, you can construct a solution which has the energy of m bubble. And you can let his m go to plus infinity. Then you get that the energy goes to plus infinity and the Morse index goes to plus infinity. And this is a very specific situation, because usually if you have blow up, so you can, for example, if you think of Yamabe type equation, or even on the Nirenberg problem on a closed manifold, you can say there is a level such that I know that all bubbles are under this level here, because you have that all the bubbles occurs only at the critical point of k. K is a non-degenerate critical point, so it has isolated critical values, and then if you know that you have simple blob, then you have some kind of uniform energy bound. But now the problem is that there is no non-simple blob, and depending on the condition that you put on K1, you can have a point where you can build arbitrary many bubbles, and this means that first there is no a priori estimate of the energy of this bubbling solution, but also there is no a priori estimate on the Morse indices, which means that this blowing up solution may create more and more topology. And this makes the variational problems very, very, very delicate. So in the last maybe 2 or 3 minutes, I would like to explain the construction, so the strategy of the construction. The strategy is not complicated, maybe somehow technical. So it's based on the Lyapunov-Schmidt reduction and combine it with some refined expansion of the gradient in the neighborhood where you want to build this multi-bubbling solution. So let me, in the next 2 or 3 minutes, say something about it. So first, you know that your problem has a variational structure. So solutions are in one-to-one correspondence to critical point of the Euler Lagrange functional, which I've written here. And then what you do is first you want to construct, so let me construct only something on the boundary. So you want to construct, let's say, m bubbles concentrated at the same point. So you define a manifold, and this manifold has a parameter. Some of them are finite, some of them are infinite. And for the finite terms, so this is alpha, lambda, x, these are really the parameter, lambda and x, this is a parameter of the bubble. So every bubble comes with a point, x, concentration point, and with a speed. And then this alpha, this is a gluing parameter, how it is possible to glue more than one parameter. And now this V, this is in the Struve decomposition, this is the part, this is the remaining part, which is small in the H1 more that you have. And then you look to this family where now you want to produce a non-simple blob. So for this, first, you have to know that all the points will converge to the same point. So this is why the distance of this point here, xi and xy, they converge to 0. But they converge to 0 with some height. So this comes from the blow-up analysis. You know that actually, if that xi will and xj both converge to z, but their distance will be comparable to epsilon at the power of n plus 2 divided by n. So and now you want to construct a critical point with this property that in this set here, and that what you do here first. So you have to look to the tangent space. You have to look to the tangent space, and now to define a new function, which is E epsilon, the sum of alpha I delta I plus V, where now V is orthogonal to the kernel of your, to the tangent space. This is orthogonal to the tangent space. And once you do that here, so you have first to minimize to V. So this is exactly what you do in the classical Lyapunov-Schmidt reduction. So you have to have a finite reduction, and for this you need to first you would like to have a solution. So if you have a solution with this constraint, because V now is orthogonal to the tangent space, you will have also some Lagrange multiplier. So this is BI, AI, and CI. So you write your equation, because now every critical point of your function will be a critical point of the function CF in the variable alpha I, lambda I, CI, and V. And then now you start with this one here, the infinite dimensional part. So this you can solve it because the second variation is because the linear operator is invertible on the orthogonal of this space here. So this you can find a solution, and you can also find an estimate of the solution. So this solution will be less than constant time epsilon. And now you are left with a finite dimensional system. And for this, you expand the gradient. This is what I said at the beginning. You expand the gradient in this set here. And if you expand it here, you see that here alpha I, this is one critical point, which is given exactly by this one here, kx equal to this one equal to 0. and then you look to all the situation. And here, the most important things here, and this is the difference, because this you can also do it on the sphere. So, and you would ask me what is the difference? The difference is exactly here. This situation here on the boundary here makes that it is possible to construct these points which are very close to each other and converge to the same point. And then now you make a change of variable. And once you make a change of variable, your system now is equivalent to a very nice system as a beta I equal to big O of epsilon log epsilon. Lambda I is a big O of epsilon as a power of n minus 4 divided by n. The Hessian equation, the Hessian at the point is a big O of epsilon square plus eta square plus epsilon square. So, and this is non-degenerate. So this you can see it as actually the norm of the psi is bigger than, smaller than this one here. And this is a typical situation when you can, where you can apply the Brouwer fixed point theorem, and you find the solution. So this is the strategy of the proof, roughly explained. So my time is over. Thank you very much for your attention.
Yeah, Mohameden, thank you very much for this very inspiring talk.